All right, so my name is Guhy. I'm here to talk about the last of the field resins, and it's specifically acrylate graphene oxide. So just a little bit of intro for you guys who don't know. Graphene is, and graphene oxide as well, are carbon-based compounds, and so it's a 2D structure of like a hexagonal shaped carbon atoms, and it's this pretty new material relatively. It was developed a few years ago. It's kind of unique because of its two-dimensional properties. It's very has specific electronic properties, electrochemical properties, as well as structurally for its size. It's a very strong material, and therefore adding it to a field resin polymer can have some pretty cool applications. Right, so the paper I read and critiqued was 3D stereolithography printing of graphene oxide reinforced complex architectures. It looks like, judging by the authors, this paper was done in Asia, but it was done with a lot of universities throughout the U.S. The main topic is a reinforced photopolymer with graphene oxide embedded in the polymer. So the main question they wanted to ask was, can this nanopolymer, can this nanofiller into this polymer increase the strength without sacrificing ductility? Because a lot of the studies previous to this had showed increases in strength, but the materials had become, the elongation had significantly decreased, the ductility was way down. So that's what they kind of wanted to experiment with. As far as the manufacturing approach, you guys know stereolithography. This one was a bottom-up process for the printing process. The polymer they used specifically, they didn't really reference as the structure of the polymer. The only thing I could find was the PIC 100 from EnvisionTech. That's the one that they used. And then the single layer of graphene oxide was embedded throughout the structure. There are 3 ways to prepare graphene oxide in a polymer. There's in situ, which is basically where you combine the graphene molecules with the polymer, and then you insert some kind of reactant that combines and allows the structures to react in situ while you're printing and form the structure. The second is liquid preparation, and then there's also melt preparation. The one they used for this was liquid preparation. That's basically where you dissolve the graphene in some kind of solvent. For this one, I think they used I can't remember. It was some kind of alcohol. They dissolve it in the solvent and then mix it with liquid polymer, and then in an ultrasonic vat. A lot of the reaction takes place in the liquid form, and then it's transferred to the printing process. The way they differentiated the factor that they changed in this experiment was the percent weight of the graphene oxide to experiment with how much graphene oxide affected the tensile properties, the strength properties. The way they measured that stuff, they did some transmission electron microscopy to look at the actual structure and how the single layer graphene oxide looked inside the polymer. They also did some tensile and compression testing and some differential scanning calorimetry, which has a lot to do with the melt and crystallization properties of the polymer. So, study 1, the main gist of the study was, can the nanofiller increase the strength without sacrificing ductility? And they did see a significant increase in strength. As you can see here, we have the 2 graphene oxide polymer peaks, and those are a lot higher than the polymer without the graphene molecules. And then what they did to kind of take it even a step further is they cured the 0.2 weight percent graphene oxide. They cured that for 6 hours in heat, and it actually increased the properties even more and gave it more strength. And that's the top curve you see here. And then this is the DSE I was talking about, which kind of shows the polymer without the graphene oxide has a melt peak right around here, and so when you introduce the graphene oxide, it gives it more of a crystallization peak up in here, and that's actually improves the structure, like I said, as they cure it over time. More crystallization occurs down here and allows it to become stronger after curing. To put some numbers on it, the tensile strength increased by 25% and 45% down here for the 2% and the 5%. And then the tensile strains, without the graphene oxide, tensile strain was about 0.19. And so when they introduced the polymers, it only took it down to 0.17 and 0.15. So it was pretty was a lot less of a ductility sacrifice than had been in previous studies. Oh, and I forgot one thing for this. The structure that they printed for these tensile strength tests looked a lot like, you know, a tensile element that you would put inside of a machine. It didn't look like some kind of, you know, box or cube or anything. They actually printed stuff specifically to go inside the machine. This is some of the TM imaging, and it kind of shows, the first one we have here is, let's see, it's perpendicular to the graphene oxide. You can see how thin they are. Even when they say perpendicular, they're kind of being generous, because you can't even see it if you get exactly perpendicular to the molecules. You have to tilt it just a little bit so you can get a little bit of a profile, because it's so thin. And then this picture kind of shows a little bit of the graphene oxide layer with the polymer. This is like a polymer crystal layer, or a crystal chunk. And then this one over here kind of shows a little bit more of the linking. And they kind of saw what they're expecting to see, in that when you mix the graphene oxide and the polymer together in the ultrasonic thing, the dispersion is kind of random. I mean, it's pretty uniform and random at the same time, if that makes sense. You can't get all the graphene oxide aligned. They're all kind of turned different ways. And so I guess that's kind of good for spreading out the stress inside of the material. And then this is one more. They did some compression testing. For these, they actually printed a structure. As you can see here, this is the one with the polymer without the graphene oxide and with the graphene oxide. There was also an example in my first slide of one of a structure that was printed with both. And so for compression testing, they really kind of saw with this that the graphene oxide filled resin can kind of accept more force, you know, with more strain. What they did see also was some limits to the structure, and in fact, both of these structures failed. I guess right around the end of their strain curve, and broke into like 5 pieces. And I think they made some conjectures as to why they failed so early, and I think, or they failed, period. And I think it was because when you have the graphene oxide embedded throughout the structure, it allows a lot more stress to be placed on the polymer molecules that are surrounding that structure, and then less stress on the ones around it. So that kind of takes away from the entire compressive strain of the molecule. Yeah, this picture shows it really well. They printed some kind of a honeycomb thing for the compression testing. You can see some of the buckling that took place when they broke into like 5 pieces. But yeah, they definitely demonstrated some increases in strain. I think it said 10% and 20% strain for the different materials. Let's see. In summary, just like the hypothesis kind of thought, introduction of these graphene oxide, and there was other papers done on just graphene by itself, but this one was specifically graphene oxide. But it did have a significant effect on mechanical properties of the polymer. And then another thing is that the properties can even be enhanced with curing. That was a big step as well. My personal critique, I thought it was useful. This was useful in making significant strides towards creating polymers that, you know, were exceptional in strength, more so than a lot of the stuff we have nowadays. Not huge strides, because you know, like I said, the demonstration of increase was only you know, 10, 20%, 40% if you cure it. But it is huge, because if we can continue to embed different nanoparticles and different materials and structures and get those strengths super high, then the limits for polymers kind of continuously grow. That was my critique. And the ease of the nanofiller embedding into the polymer, I thought was really easy. You know, they didn't have a thorough discussion of how it was actually done, but to me it just sounded like they had the liquid polymer, put this stuff in a solution, and just turned the ultrasonic thing on for like 30, 40 minutes, and then it was done. And that seemed pretty convenient to me to get these kind of increases in strength. So.